So, yeah, thank you for coming to our seminar. So let's get started our seminar, which is a 38th Professional Geoscience Seminar organized by the MPTI team. And as all of you know from our announcement poster, today's guest lecturer is Dr. Astin Nurdiana. And first of all, dear Astin Nurdiana, thank you very much for accepting our invitation. And she's an expert in the fluid rock interaction, metamorphism in the mid-crustal depths. And currently she is working as an assistant professor in the Tohoku University, Japan. As we know, fluid and fluid rock interaction in the mid-crust are main subject for economic geologists and metamorphic petrologists. So today she is going to talk about the fluid rock reactions and porosity generation induced by the infiltration of the pegmatic fluid at the mid-crustal depths. So it is my great pleasure to introduce Astin. And in 2015, she got the bachelor degree as a Geological Engineering Institute Technology Bandung in Indonesia. And in 2018, she got the master degree from the Tohoku University, and her thesis title is Migration and the Reaction of the Magmatic Fluids Related to the Granitic Pegmatite Complex in the Kinkaze Island, northeast Japan. In 2021, she got the doctoral degree from the Tohoku University, and her thesis title is Fluid Rock Reactions and Porosity Generation Induced by Infiltration of Pegmatic Fluid at the mid-crustal depths. So she published the two papers as a first after, and I would like to invite Astin to start her today's talk.
Okay, thank you, Osgo. Good afternoon, everyone. Now here is like afternoon time in Japan, Sunday. And yeah, I'm Astin. Nice to meet you all. So thank you for MPTI team for having me today. Yeah, I'm really great to know that you have this kind of active community to really support for those who interested in earth science. Hope your community gonna last for a long run. Maybe I'll go.
Thank you.
For this community. Okay, I'm gonna share my screen. We already see some of them. Put fluid and rock at the same place and the same time under high pressure and temperature. And yeah, that's the way to simulate to get more understand on how a fluid and rock working in deep crust. So that's basically what I'm doing now, and I want to share some of my thesis work for you. So I graduated last 2021 for Ph.D. program, and I belong to International Environmental Leadership Program here in Tohoku University, and now I'm currently working to help my sensei at the same lab. And yeah, I come from Indonesia, especially for Java Island. Hi.
Sorry, Astin. Can you? I cannot see your slide in full.
I see. It's not.
Yeah.
Showing. Okay. I try different settings.
Okay.
How about now?
Yeah, now it's okay. Yeah.
Okay, good.
Thank you.
Yeah, I come from one of the most populated island in Indonesia, Java Island here, and you can see in the next island, in the east part, it's like Bali. It's like very famous, highly tourist destination around the world, I guess. And you can try to go to Bali and then enjoy 3D beach there. And yeah, I love traveling, and then spicy food. It's really spicy food from Indonesia, one of the best food Indonesia has. So if you want to try, you can try. at least once in your lifetime. Okay, and now I'm going to start my presentation with a bit introduction. So my research actually comes from the importance of the fluid reaction for transferring energy and element. So basically, this work is a small part of big project to understand the how to say high pressure temperature condition under Earth to for exploring the potential for supercritical fluid in geothermal area. But it's like really small part of that big project. And yeah, I'm mostly working in granitic system. And as you can see here, above the granitic system, we supposed to have, or uh, we can find a pegmatite body here. So it's kind of faint. They have similar composition with the granitic itself. And this pegmatite, it's inferred to be like mostly fluid. So they have like solid and then fluid. And yeah, and above this granitic system, the fluid can be flown frequently through fracture or metric flow. I don't know, maybe some of you already know about this metric flow, especially grain boundary, macrocrack, and transient porosity. And under hydrothermal experiment, for grain boundary and macrocrack, they tend to have more capability to transfer the fluid compared to the transient porosity or smaller pores they come through this grain. So, for example, this is grain boundary, and if fluid coming, the fluid will automatically come through this grain first, and then they distribute it through this grain boundary you see by the small pores. But at the higher temperature, higher pressure at the deep crust, this grain boundary is inferred to be close or really tight. So it's as tight as difficult to through any fluid coming. So for example, like this one, so it's really close. So that's why at the deep crust, there's possibility that we can find the other fluid pathways, for example, like macropores. So macropores is the one, how to say, dominant candidate for that, the fluid pathways under mid lower crust. And we can find these micro to nanopores in almost all of the alteration or replacement mineral. And yeah, there's a lot of example of these pores occur along with the replacement, such as in feldspar and then calcite or ilmenite, and there's pretty much a lot of experiment on and natural study on this phenomena or these pores, but they're still limited. So the universality of this micropore is still questionable. So yeah, I want to try to figure it out. So, and in the mechanism of this porosity generation or transient porosity is also still a lot of questions. So basically, the formation of these micropores is by coupled dissolution and precipitation. So if maybe you have heard about this, so when, for example, this albite replaced by potassium feldspar, so in this area, the fluid dissolve this part, this mineral albite. So it's initially albite, and then precipitate at the same site, this area. So it's like dissolve and then precipitate, dissolve, precipitate from outer grain up until inner core of the grain. However, the effect of the fluid and rock composition toward that reaction, this specific reaction, is still understudied. So that's why we want to know how is the mechanism of macropore formation, especially in the reactive fluid in granitic system and in feldspar replacement for my studies. And the big objective of this is to understand the mechanism of network formation, the infiltration of pegmatitic fluid, and its implication to crystal hydrology and current geothermal field. Yeah. So this is the outline for my presentation. Actually, for my latest paper, so it's mostly explain about the outline number 2, 3, and then 5. So that's why I skipped number 4 because that is different part. So basically, I'm going to explain the natural rock sample description, and after that, calculating for the porosity, and then calculating the reactive fluid. After that, the implication. Implication means how the effect of the spectral porosity to increase the permeability under the crust. So the general studies like this, so natural sample observation and then hydrothermal experiment, but we're going to skip this for today's presentation. So the natural sample observation, I conducted several analyses from EPMF, HDSAM, 5DSAM, and then LACPMS, and then fluid inclusion. For LACPMS, it's not. That's I will not mention about that because that's in the other study. So maybe it's only up until ABC EDS. And then, yeah, the main study is like about petrography and mineral composition, then mass balance analysis, and mostly PP condition estimation and porosity description. So, yeah, by the end, I want to know the micropores development during the reaction. And the next is about the pegmatite and metamorphic condition rock in Kingasan Island. So for this chapter, actually, I want to show you how I can get this figure. So this figure explains that this is like granitic body with quartz diorite composition and has this condition when emplacement. So when it's getting cold, it has this heaty condition, and after that there is pegmatite as well in the roof of this intrusion and have this condition, this heaty condition. And yeah, I want to show you how I can get this result. So basically it's what I'm looking for this chapter. Yeah, this is the general information about the pegmatite. Maybe some of you have already known about this. So actually pegmatite has a similar almost similar composition with the granite itself, but it has the order of the mineral formation from wall of the vein. Mostly it's in a vein or dike, and come through into the center of the dike or vein itself. And it's known for the source of strategic minerals, I guess, like industrial minerals, such as the feldspar, and then the other rare metals as well. And the one thing that's interesting for this pegmatite is like the late stage of pegmatite of the reactive fluid, which can increase the porosity of the wall rock or the rock around the pegmatite. So the fluid the pegmatite bring along, it's really reactive. So we can learn about that, and then we can maybe understand, and we can use that reactive fluid to be to be applied in the other permeability increase way or permeability increase experiment. However, the extent and the effect of that reactive fluid should still remain unclear. So I want to know how about if I can find that reactive fluid, and then how we can use that composition. So it's in this study I do the detailed petrography microstructural analysis, and then after that doing the PT estimates of that fluid rock fraction. And for geological setting, this is the Kingasan Island. It's in Tohoku area or still in Miyagi, Sendai, around 3 hours drive here from Sendai. And yeah, my sample was taken from this area, and this is the drawing image. So we've got granite, and then this is the pegmatite across that granite. And then yeah, this is the Cretaceous granite bodies, and as you can see, this is the quartzite, and then this is the pegmatite, and then apply we call apply for the smaller vein for the pegmatite, but basically still is similar composition. And around that pegmatite, we have interesting metamorphic rocks from biotite schist or mafic schist, and we also can see, even though it's not that really clear, but there's like boundary for both bodies. This is pegmatite and biotite schist, and then you see some of the outcrop image of the sample. So we have like this quartz steroid, and then this is biotite schist, and the biotite schist is intercalated with the mafic schist, and also sometimes we got pegmatite cross parallel into that metamorphic rock. So you can take a notice that this is the schist that we have like biotite schist and then mafic schist, and some of them show the reactive zone, reaction zone, and from this we can really learn the the formation condition. And yeah, this is the simple description of the pegmatite itself. So under the microscope, you can see clearly the composition. Actually, it's enough to see by the hand specimen, but we want to know the detailed composition. So we see under the microscope, and yeah, you can see there's a lot of garnet here. And yeah, garnet is really helpful for the other study, but I will not mention that a lot in right now. And yeah, you can see that this is the wall, and then this is plagioclase, and it's also plagioclase. So there's like order of the growth of the pegmatite, and this potassium feldspar, of course, it's always the the order of the crystallization in pegmatite. So yeah, this is the biotite schist. Biotite schist is mostly quartz, plagioclase, and biotite, and this is pegmatite and biotite schist. Yeah, and the other schist is this is mafic schist. Mafic schist, I have several different compositions based on the hornblende, the occurrence of hornblende or clinopyroxene. So I have a hornblende, clinopyroxene, then actinolite. So it's amphibole schist, and yeah, they have pretty much mineral assemblage, different mineral assemblage that we can see, and different mineral assemblage means we can use the different mineral pairs for PT estimation. And this is clinopyroxene, has reaction zone, and it's really interesting. Yeah, I will recall about it later. And one thing that important here is not all of the bulk composition has quartz. So for this two has quartz, but for this one it doesn't has any quartz at all. And it's very important to have some implication later for porosity generation. And yeah, this is the first thing I have to do for this sample is identify like which composition it belong to for this amphibole and then plagioclase. So for the amphibole composition is the cation site, so the composition is hornblende and actinolite. This one, it's come from different bulk rock. And then for the plagioclase, it has wide range of composition, but yeah, mostly it's here. For different wide range composition because it comes from different sample, but basically per sample have pretty similar composition. And for the clinopyroxene case, you can see there's a clear reaction zone here, the dark bluish greenish here, and it's really show the different composition due to the replacement. As we can see, this is the mineral modes from this pegmatite up into this host rock. This is the host rock and the area of the direction, so it's only this one, and then the rest is host rock. So from here we can see there is like occurrence of hornblende only in reaction zone, but it's difficult to see that in this host rock. Yeah, there's like, but not much. And that's really help to understand or to calculate the mass balance. So there's like two kind of replacement here. So kind of reaction replacement and then plagioclase replacement. I will explain about it later. So, and for the other keys, it's replacement as well. For example, this is first feldspar replacement. They show a lot of pores. It's really intense pores, and this is as well, but not that clear. And it also replaced some replacement here. Yeah. So moving forward to the PT estimate. So after I got what mineral assemblage of my sample, I try to calculate the PT estimate. So I will not explain about this right in the right side because it's a different sample. But yeah, for hornblende plagioclase, for hornblende case, I try hornblende plagioclase thermometry and aluminum in hornblende geobarometry. Maybe some of you already use it for a long time. And this is what I got. Condition for the crystallization for this forest diorite. And yeah, after I got this with estimate, I plot in this. But this is actually fluid inclusion study, but I will not mention about this. But yeah, I got quartz diorite emplacement here condition, and after that followed by the pegmatite fluid infiltration here. So by the end, I got this quartz diorite emplacement condition around 600 to 700 degrees C, and then under this pressure. And for the pegmatite, assume to at the same pressure, they have lower temperature when infiltrated into surrounding metamorphic rock. So that's for this chapter. And the next is the porosity generation, and it's induced by the infiltration of pegmatite fluid. So this is the let's say the schematic figure that we can got from this chapter. So I will explain how I can get stage first and then the stage 1 and stage 2. So at least there is two stage with different fluid composition. For this stage 1 is like sodium rich fluid, and then the second potassium rich fluid. And I will explain how can I drag the conclusion out of this, all of this sample, all of this data in this chapter. So it comes from the porosity generation who become the interest of the recent studies, really because it really helped the researcher to explain that there is a lot of fluid migration at the mid or deep crust, but we know that deep and mid crust is known for having very low permeability or even impermeable, but we still have a lot of fluid there. So it's assumed that maybe there's one specific way how the fluid can be stored, and porosity, micropores, is the one who can explain that. But still, we need a lot of evidence to really prove that hypothesis. So yeah, so the natural micropore generation in relation to various fluid sources is poorly constrained, really. So yeah, for this study, I analyzed the element transfer and micropores bearing replacement to understand that how this, in what condition these pores can be formed, in which fluid and rock composition. So I did detailed petrological and microstructural analysis on mafic schist and pegmatite and a sample from Pingasan Island, and then determine the multi-stage fluid infiltration and will come along with the core networks. And the first method I use is like mass balance analysis. So basically, we want to know before replacement and after replacement composition. So if you have like before host rock, we compare the host rock composition and then altered composition. After that, we subtract part of them and then we cut the extra number of certain element, and that's possibly the composition of the fluid. Okay, and after that we make visualization of the micropores networks using FI descent. So FI descent, so it's actually the micro excavation and direct chemical analysis of the micropores. And for the mass balance analysis, so this is the example. So you can see in this reaction zone, there's a replacement or Kleiner fraction into hornblende here. And then also replacement or calcium plagioclase into sodium plagioclase here. And by these two replacements, we want to know what kind of fluid they infiltrate into this bulk rock that can create this reaction zone. So the first is from clinopyrazine replacement into hornblende. So this is the calculation, and you can get gain element for this one. So how to read this is really simple. For example, in this calcium oxide, so we don't gain anything, but we lose calcium oxide. It means that calcium oxide, calcium loss from this system, and then we got this gain sodium and then water for this one. And so yeah, for the micropores bearing sample in this analysis case, so we can see that the replacement is really intense and come through the all grain, really like it's even cross the grain. So maybe it's kind of like 3D fluid infiltration into the whole part of this bulk rock, but it's only affected to the plagioclase, not to the actinolite. And there is also for plagioclase, we also wanna make it detailed. So we compare the actinolite with aluminum pure and then actinolite with aluminum rich. And this is mass balance for this actinolite. So we get gain of the sodium, and then sodium, no sodium, get the sodium and then potassium and then silica, and a lot of lost aluminum and calcium. It is one. And I want to show you, this is the micropores networks that get. So we excavate this line A to B, and then we see the 3D, we construct the 3D image. So we cut area along A and B, and we out of like 500 figure profile from the A to B, we construct this 3D image. And from this 3D image, we can see the porosity of plagioclase grain is around 3.5%. And if we assume that plagioclase is almost 40% of the rock, so we can get the bulk rock porosity is around 1.34%. And you can see that this porosity is really angular and then disconnected for this one. And yeah, after micropores, so I will remind you again about this mass balance analysis. So after we got it for mass balance from each sample, so we're gonna calculate the total gain on loss for all. So for the planoparesis case, it indicates the sodium-rich fluid infiltration, and then for the aqueous case, so the potassium-rich fluid infiltration. That's simple. Sodium-rich, it means not only sodium, but maybe with still silicon and aluminum and so forth. So at the first, we already have PT condition for granite emplacement, and then also for pegmatite, and also for the replacement, we can use, for example, aluminum and hornblende geobarometry, and then hornblende plagioclase, and then two-phase for thermometry also used for not only for pegmatite and granite, but also for the replaced mineral. So this is the condition for actinolite and then hornblende case, and this is the reaction zone emplacement. And yeah, after that, this is the kind of reactions described. The reaction zone works to place in this condition. And then for the this plagioclase replacement, plagioclase replaced into albite and potassium feldspar, which bring a lot of pores. This is their condition for the formation at the lower temperature, assume at the same pressure. So from here we can see there's kind of two area of the PT emplacement. The first, stage one is related to the sodium-rich fluid infiltration in 600 up until 700, and then the second stage is plagioclase replacement with potassium-rich fluid at 400 up until 570 degrees C. Right. This recut, yeah, and this fluid infiltration can also followed by the loss or the moving out of several elements into out of the system. And one thing that we can take a note is like the micro to nanopores were formed due to the feldspar replacement, especially in stage 2 in potassium-rich fluid infiltration. So potassium-rich fluid can be we can call it as reactive fluid to generate micropores in this study. So yeah, this is a schematic figure like the stage 1 and then stage 2, and in which they are replaced. And then the next is still have one. And the next is I jumped to chapter 5 because yeah, right away into the implication to the fluid flow within the crust. After we got that, okay, we know that some reactive fluid can generate micropores, and then what happened then underneath? So we want to know if these micropores is really have implication with the crystal permeability or not. So it's actually the introduction for the yeah, why this micropores is really important, because yeah, we in this supercritical geothermal, micropores can help to extract or can help to store energy which can be extracted. Because yeah, as I mentioned, that in the supercritical geothermal field and depth of 5 kilometers, it's inferred to have really low permeability, and if there's a lot of pores, the energy can be saved, and then maybe we can extract all of that. But yeah, that's really ideal. So we want to know how's the best practice of what's the really happened there. And then yeah, I use the Kakona geothermal system as the place to understand if the if there is really feldspar replacement in the supercritical area or not, in the supercritical geothermal or not, because Kakunda is known for the geothermal field, and they're still active until now. And we have Japan has ever make the well, really long well, up until active granite. Here, the younger granite found in this world. And if we can find any feldspar replacement around this granite or at the roof of this granite, so it's really similar to what King Kazan temple have. So this granite, and then on the top of that we have a plagioclase or feldspar replacement. Yeah, and then I can find in this depth, I can find some plagioclase replacement, but yeah, still have to really doing some studies detail about this. So some reference also ever mentioned about the occurrence of this feldspar replacement and then the occurrence of micropores in this area. And yeah, this is the example of the micropores. And if we really compare with the geophysical study, so we can see that this we can find a lot of micropores in this area. So yeah, we can find that micropores for supercritical geothermal field zone. And this is the after I got porosity from the micropores, the current of micropores, so I assume that the micropores connected or transient. So we can calculate the permeability that can be generated from that feldspar replacement or in the occurrence of the micropores. So this is the background permeability, and using this formula, I can get the permeability due to the micropores network can increase up until this order to 4 order magnitude. So this micropore of these studies, and this is some picture studies. Yeah. So at this step, 11 to 16 kilometer, we can get the increase of variability 2 to 4 orders if they have fluid that can replace the mineral and generate micropores. So yeah, it's some schematic figure if we have micropores network in active geothermal field. So when there's like fluid coming through the surrounding metamorphic rock, so they will be deposited or precipitated along this vein, and yeah, until the vein is really closed. But after that, with the pervasive fluid transient porosity or with the micropores, or if as long as the fluid still come through this sample, we will still have micropores, and even the micropores can be found until this sample exhumated into the surface. That's what we found from the Kinkazan sample. So even though they're already exhumated and then the pegmatic already sealed, already closed the vein totally, you still can see the micropores. Okay. So it means that micropores can be really a thing for in terms of fluid pathways under high pressure temperature condition. Maybe that's all. If you have any question. And yeah, I'm sorry, maybe I explained too fast, or if you want me to explain one more thing, it's okay. Or repeat some part, it's fine too.
Yeah, thank you very much, Astin.
Yeah,
So yeah,